In this session, we discuss clearance analysis to predict the obstruction loss, if any. It is useful now to clarify the convention used to define path clearance, denoted by CL. It is self-evident that an obstacle below the Fresnel ellipsoid axis produces a positive clearance, to be expressed in meters. On the other hand, the figure shows that if the obstacle is above the Fresnel ellipsoid axis, then a negative clearance is measured. Moreover, we have seen that we are interested in the amount of the Fresnel ellipsoid that is obstructed. So, the normalized clearance is defined as CL over the Fresnel radius F1. Fine. Now we are familiar with all the basic definitions and concepts that allow us to complete the clearance analysis and to estimate the power loss produced by an obstacle. Vertical refractivity gradient, ray bending and K-factor, Fresnel ellipsoid as a volume involved in radio wave propagation, and finally, normalized clearance. On this basis, it is possible to carry out a precise theoretical analysis of diffraction loss produced by an obstacle, when the obstacle has a well-defined idealized shape. Two examples are given. First, knife edge obstacle, that is, an obstacle with negligible thickness along the path profile. Second, the smooth spherical earth, that is, the obstruction produced by the Earth's surface for transmission beyond the horizon. Other cases, like rounded obstacles or multiple obstacles, need a more complex and approximate analysis. In the figure, you see theoretical and empirical results about the obstacle shapes that we have just mentioned. Knife edge, smooth spherical earth, and rounded shape representative of hilly terrain. The first comment is that the obstacle shape plays a significant role. For a given value of normalized clearance, the diffraction produced by a knife edge obstacle makes the loss limited to a value much lower than in the case of propagation beyond the horizon. Look at the case of zero clearance. This means that the top of the obstacle touches the ellipsoid axis. Half of the Fresnel ellipsoid is obstructed. In this case, the loss produced by the knife edge obstacle is just 6 dB, while with smooth spherical earth the loss is much larger, about 14 dB. Moreover, let us consider the case of normalized clearance equal to -1. This means that the Fresnel ellipsoid is totally obstructed. The loss is very large, particularly with the smooth spherical earth obstacle. However, the signal is not totally cancelled. As a result of this analysis, we are going now to see how the ITUR has defined a procedure to check path clearance in temperate and tropical regions. The first step in the procedure to check path clearance is to define K-factor values. For standard conditions, the usual value is 1.33. The minimum value can be derived from the figure we've previously seen, in order to take account of path length. As an alternative, it can be assumed from previous experience on propagation on the same radial path. In this table, you see the detailed criteria from ITUR. The state standard K-factor means that the corresponding criterion is applied most of the time. In this state, it is required that normalized clearance is greater than 1. That is, the whole Fresnel ellipsoid must be free from obstructions. The minimum K-factor criterion will operate under extreme atmospheric conditions. As you can see, in this state, clearance criteria are more complex, depending on climate and terrain. It is accepted that part of the Fresnel ellipsoid is obstructed. Now, we see some simple examples of application of the ITUR clearance criteria. Here you see how the ITUR criteria can be applied in the case of standard K-factor. The figure shows only the lower part of the Fresnel ellipsoid. The grey line is the ellipsoid main axis, with the curvature corresponding to K equals 1.33. The criterion says that the ellipsoid must be totally free from obstructions. So, nothing along the path must be above the red line. In this case, path clearance is verified. Similarly, in this figure, you see how to apply the ITUR clearance criteria with the minimum K-factor value. First of all, a lower K-factor produces a greater curvature of the ellipsoid's main axis, plotted as the grey line. Moreover, only 60% of the lower part of the ellipsoid is required to be free from any obstruction. This is shown by the red line. Again, nothing along the path must be above the red line in order to satisfy ITUR clearance criteria. A final comment. If we can compare the ITUR criteria with the estimate of obstruction loss, which we have seen in a previous figure, we observe that, in some cases, the ITUR criteria may not be satisfied even if the obstruction loss prediction is 0 dB. As for example, in the case of normalized clearance 0.5. This result simply shows that the ITUR criteria are quite strict.